Number 2A. So the question says, so y'all have your homework out, you got your notes out, you got all that stuff out because you've been waiting patiently while I got myself organized here. Question 2A says a bag of sugar has a mass of 2.26 kilograms. Okay. What is its weight in newtons on the moon where the acceleration due to gravity is 1/6 of that on Earth? Okay, so let's do it. Let's figure it out. Let's try and figure out what in the world it's talking about. Here we go. New page. So it says that it has a mass. This is again number 2 on page 143. Its mass is 2.26 kilograms. It says, what is its weight? You read the word weight and you interpret that as what? What does weight really mean? Not mass. Oh, if we don't remember that, we're going to be in trouble. Let's take a look. Yeah. If we go way back up here. Yeah. The force of the whatever, the planet, the moon, the whatever, on an object. That is this thing called weight. I just don't use the word weight because it doesn't mean a lot to me, but I like this better. So really when they say what is the weight, they really mean what is the force of the moon on the bag. Okay, that is the weight. And it says that the acceleration due to gravity, A sub g, is equal to 1/6 of, I don't know why I wrote a 3. 1/6 that of what it is on Earth. Okay? 1/6 of negative 9.8. Is that okay so far?
What's the answer to the problem?
I don't know, but I can look for you. Maybe. There it is. 3.7?
Yeah.
Is that what you got?
Newtons?
In newtons. Mm-hmm.
And it's not negative, right? Or is it
negative? So generally when we talk about weight, we talk about just the magnitude, the size. So yeah. So kind of like if I asked you what is the force of gravity of the Earth on you, you could say 125 pounds, or you could say negative 125 pounds, right? Because it's actually pulling down. But if you're just talking about your weight, you might say just that number. Yeah. Does anybody want me to go through that, how we got that number of 3.7? Or is everybody okay? I'm happy to do it. I just need like a wink and a nod. Yes? Yes, let's do it. Okay. So the force of the moon on the bag of sugar. So I'm going to go back to my little notes here in my force inventory, for example. Okay. I'm going to take the mass times the acceleration. In this case, the acceleration is not 9.8. It's 1/6 of 9.8. So we're going to say the mass times 1/6 of 9.8. So that's going to be the 2 times 1/6 of 9.8. And that gives us the 3 point, what was it? 3.7. Is that okay? The second part says, what is the weight on Jupiter? So there's a problem with that. Number one is that Jupiter doesn't have a surface. But yeah, if you happen to be sitting right at where we define the surface of Jupiter to be, okay? Yeah, it's like 2 point something more? 2.64 times more than the Earth. So you're just going to take 2.64 times 9.8. Yeah.
Number 5 was a thinker one.
It was a thinker one.
Yeah.
You love the thinker ones, right? Hi. Do you have a pass by chance or no? Oh dear. Okay. Yeah, I like this thinker question. So we're looking at page 129, number 5, this one here. It is a thing. It even says critical thinking right above it, so you know that it's going to be a thinker question. Can an object be in equilibrium if only one force acts on the object? What does it mean to be in equilibrium? They're equal, right? So you've got like two forces pulling it, right? So is it possible to be in equilibrium if there's only one force acting? It'd just go in that direction, wouldn't it? Yeah. Is it possible for an object to be in equilibrium with three forces acting? Yeah. Ryan, why do you say yeah? Then we did it. We had one like that, didn't we? Yeah. Yeah. Sure. Yeah. So as long as the forces add up, so if you have a box and you have one force pulling down and you have two forces pulling up, they can add up to 0, right? Yeah. You can have any number of forces that you want to add up to 0 except just one force. Because one number can't add up to 0 unless it is 0, and then it wouldn't exist, and then we're back to the beginning of the story. Yeah?
Okay, so you have like a really big ball, and it takes like 500 newtons to move it. You're pushing with a force of 499.
Yeah.
It's not moving, it is about equilibrium.
Yeah, because it's not accelerating. Anytime it's not accelerating, it's in equilibrium. We're gonna talk about that in just a second. That is the topic. Yes. Did number 1 go okay, or do you guys have questions on that one? Okay.
Speed through it.
Just do it. All right.
Speed through it.
Speed through it. Is that what you said? No? All right. So yesterday we were like at this like big moment, and then the bell rang. Silly bell. Happens to me all the time. All right. So let's remind ourselves of what we were doing. We had a ball, and we rolled that ball, and we looked at 4 different situations, right? And this is going to get exactly to what you were just asking. So in case A, what was happening to the ball? Do you remember? It was sitting at rest, and we didn't write that down. So let's write that down right now so we don't forget. In case A, the ball was at rest. If the ball is at rest, is the ball accelerating? No. So I'm going to say that the acceleration is equal to 0. What do we know about the forces acting on the ball in case A? The normal force acting up and the earth or the gravitational force pulling down. What do you know about those forces? We've talked about it a few times. What's that? They're equal? They're equal? So that means that if we add them together, F net equals, so that's Fn plus Fg. Oh, but Fg is pulling down. They add up to 0. Yeah?
Does equilibrium only apply to the y direction?
No. It applies to both directions. But in the cases that we've talked about so far, we've only really been talking about in the y direction. Right? But we'll get there today because we're going to do some ranking stuff that'll get you where you need to go. Does that sound good? Yeah. So we could say in case A, I want to make sure that you're writing all this down, right? The ball is at rest, the acceleration is 0, the net force is 0, and we could say that ball is at equilibrium. Okay. Remind me what was going on in case B. What was happening in the story of case B? Either think about that from yesterday or look at the free body diagram. What was going on in case B?
You gave it a push.
I gave it a push, didn't I? And my hands were in contact with the ball. Okay, so that's just going to be kind of our like, oh yeah, that's what we were doing. So I pushed the ball. So Miss K pushed the ball. Was its acceleration equal to 0? What does it mean to accelerate? Speed up or slow down, right? Either way, acceleration means a change in velocity over time. I'm just going to remind you of that. Acceleration is a change in velocity over time. Is that okay the way I wrote that? I think we've talked about it like that before. Triangle means change in. So the change in velocity over time did not equal 0. And we know that because what was the ball doing as I pushed on it? It moved, it rolled, and most importantly, what did it do? It increased it in velocity. And we know we really just care about it changing in velocity, right? But absolutely, it changed velocity. In case B, and this kind of talks to what you were asking about, Jordan, but kind of not too in some way, we would add up the net force in the y direction. That still equals 0, doesn't it? But what about the net force in the x direction? Is it equal to 0? How many forces are acting in the x direction? Is it possible to have an F net of 0 with just one force acting? Is it possible for an object to be in equilibrium with just one force acting? No, we just did that problem, right? That was the critical thinker question that I just had to do for homework. So no, it can't be. So this is one of those things that I just want to make sure we're kind of getting sunk into our brains. Equilibrium, F net equals 0. They mean the same thing. Equilibrium, F net equals 0. They mean the same thing. So F net in the x direction is not 0. We're going to say it's not in equilibrium. And then when you're taking notes, we're going to leave a space down here because we're going to write something down there in just a minute too. Yeah?
So it's not in equilibrium in the x direction, but it still is in equilibrium in the y direction.
Indeed, because it's not accelerating up or down.
So can you just say it's not in equilibrium in the x direction?
I can. Generally, when you say equilibrium, it means kind of like overall. Does that make sense? But you could say that. You could kind of parse it out to the two. That would be okay. Generally, when I think of equilibrium, I think of like overall. Is it in equilibrium? So it's either yes or no, not just like partially. But if you like to think about it that way, it's not incorrect to say that. Okay. How about letter C? I'm going to move this guy over a little bit. Just because I've run out of room. What was going on in letter C?
It was rolling, but there was nothing touching it. It was rolling, so you only had up and down. So it was that.
That's awesome. Did you guys catch what she said? Mira speaks really quietly. Do you want to say it loud or do you want me to repeat what you said? But tell me if I'm saying things that are not what you said. Okay. She said it was rolling. First of all, does that sound correct to everybody? But how many people were touching it? No people were touching it. So the only things that were acting were still just the normal force and gravity. Okay. Those are the only two things acting. So I'm going to write down what's happening first. That it was, sorry, I just get paranoid. This is, go away. Can I get you to go? There we go. So the ball was rolling. Nobody's touching it. Remember what we said we were not going to include in this story? Friction. If there is no friction, ladies and gentlemen, I want you to look up at this picture. This was really bothering people yesterday. I hope that you had enough sleep not because you were thinking about this question and this weird thing. The ball is rolling. Is the ball accelerating? Is the ball accelerating? Is it speeding up or slowing down? We assume there's no friction, right? What would be causing it to slow down? We're taking out friction. We're taking out air resistance.
There's no acceleration.
There's no acceleration. There's no acceleration. But the ball is moving. Are you with me there? The ball is moving, but it is not accelerating. It's not speeding up because it doesn't have a rocket pack on. Okay, there's nothing pushing it. It's not slowing down because we're trying to get rid of that friction idea, right? And there's no air resistance. There's nothing slowing it down. There's nothing speeding it up. So is the ball accelerating? It is not. How many forces are acting on the ball? 2, right? There's nothing else pulling or pushing on it. There's nothing else pulling or pushing on it. You're with me there? Okay. So if I write down my F net equation, There's only in the y direction. I've just got normal force, and I've just got gravity. Gravity's opposite normal. The net force is 0. This is the weird one, you guys. This is the one where I always have students saying, that is wrong, Miss Carveling. That does not make sense in my head. But I asked you at the beginning of this unit to get rid of those ideas that people have told you before, right? Not because they're wrong, but because I think a lot of times when you learn those, you don't learn them with a clear understanding of what's going on, and so you try and assign different things to a situation that don't really exist. A force has to be an interaction between how many objects? 2. So you have to have something pulling or pushing if you're going to have a force. Okay? The only 2 things pulling or pushing on that ball right now are the earth pulling down and the floor pushing up. You with me there? Is that okay? Nothing else is acting. The ball is moving. And the ball's just gonna keep on moving. Because there's nothing slowing it down and there's nothing speeding it up. So it's just gonna keep on keeping on, right? Okay? We did not need Isaac Newton to tell us that. Okay? The cave people that were living in caves and rolling boulders knew that. If it wasn't muddy and they had a nice dry surface, they could roll that boulder and it would just keep going. Are you with me there?
So
Okay.
is it in equilibrium?
I'm asking you, is it in equilibrium or is it not?
Yes.
It is in equilibrium because the net force is equal to 0. It is in equilibrium. It's weird. For the last decade when I've been teaching this, people don't want to believe me, but if you back up and you think about it from the fundamentals, this situation and this situation are exactly the same. Okay? You look at this picture, case A, and you look at case C, and there is nothing different between them. But that isn't in the picture and we don't care about it. It's not changing its speed. It's not speeding up or slowing down or changing direction. It's not accelerating. You with me there? It's weird. But it's true. Okay?
So we're not taking into account any friction.
Nope, no friction today.
Oh, yeah.
Tomorrow or Monday, sure. But not right now. And I want to make sure that you understand that an object that is moving, as long as there's nothing speeding up or slowing down, looks exactly like and will have the same situation as this one would have. It's the same darn thing.
So we have to get this stuff before we get the other stuff.
Yeah. This is it. This is it right here. This is the big money stuff right here. Yeah. Yeah. What's that?
This is it, Chief.
This is it, Chief. You got it. You got it. Okay. We did not do case D yet, did we? We ran out of time before case D. I'm not going to get the whiteboards out right now because I think we can do it. No, I am going to get the whiteboards out. Talk about case D real quick. Talk about case D with your partners. Yep. And we get rid of all that stuff because it makes our life easier, right? When you start incorporating all of those other pieces, then you have to start to reduce that. Not today because there's no calculus prereq for this class, and you can understand physics without the calculus. All right, so I want you to draw free body diagrams for case D on your board right now, please. We don't chat.
She stopped the ball. No. When she stopped the ball.
Who got up here and stopped the ball for me? Who was that?
Mira.
Mira did. Oh yeah. She did such a good job stopping that basketball from rolling. She's a rock star.
At least I'm proud of something.
You should be proud of a lot of things, my friend. There is so much to be proud of. She totally did ask for it, and I'm totally gonna have to dish it out.
Really? Shut yourself up for that.
She knows she did. It's okay. All right, draw out that free body diagram. Everybody talk. Everybody understand. Everybody do physics. I love this stuff, you guys. This is like it right here. This is why I do what I do. I'm going to ask you to put your boards up in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Put it up, put it up, put it up, up, up. Let me see. Mira's got to play. Mira's in there too. Mira's another object in our story.
I'm not even sure if it's an object.
Well, we're between two objects, right? She has mass. She is an object in my story.
It's my friend is too.
All right. Let's see. Alex, tell me one of the forces acting. Gravity, which way does that one go? Down. I'm going to be lazy because I want to go fast because I want to do more stuff. Gravity's going to pull down. Let's see. Ryan, what's another force? FN, where does that one go? Oh. Force of the surface. Okay. And then Miss Josie, what's the last one? Force of Mira on the ball. Which way does that one pull or push?
So like rolling this way.
Given my picture.
So we drew the arrow on the left side. Your left, yeah.
This way?
Yeah.
Because why?
So we thought since when she stopped it with her foot,
Yeah.
and so it hit.
Yeah.
It went technically like a little bit that way, and then she grounded.
Yeah. That's true. That's true. And honestly, guys, I just want to make sure we're all having this conversation. Yeah, so there was a lot of like things that happened, right? But I want to know like right when she actually had contact with it. That's really what I care about. Because then the rest of the story, that's a whole, I mean, like we could be drawing free body diagrams forever, right? But yes, so there was a moment when Mira had contact with the ball. And when she had contact with the ball, was she applying a force on the ball? For sure. And the force that she applied on the ball, did it cause an acceleration? Did it cause it? What does it mean to accelerate? Change of velocity. Did you change the velocity of the ball? Yes. Yeah, you did. It was going, and then she stopped it. Right? So absolutely she did accelerate the ball. It was a what kind of acceleration, Malik? You just said it? Negative. But honestly, we could just say she accelerated it. Because in our heads now we're saying that acceleration just means change in velocity. Negative, positive, it doesn't matter. I mean, if you want to say negative because it makes you happy, that's totally fine. But I'm going to say for sure that the ball stopped. Emma, do you want to go close that door for me? I would really appreciate it. Thank you. The ball was stopped. Did the ball accelerate? Absolutely it did. The acceleration was not equal to 0. We're going to look at this again in the y direction. Is there a net force? Fn plus negative Fg adds up to 0. So there's no net force in the y direction, which means that there's no acceleration in the y direction, right? It's not accelerating up, it's not accelerating down, but the ball is for sure accelerating. Which direction is it accelerating in? If it's not the y, it's in the x direction, right? F net in the x does not equal 0 because we know that Mira is applying a force, the force of Mira, or you could just say it's an applied force. That's okay too. But we know that it's not 0. Oops, I should put a not equals 2 there. Okay. And therefore we would say that the ball is not in equilibrium. So this is right when she stopped it.
So the ball stopped.
The ball is stopping. Yeah. If the ball stopped, then we'd be back to case A.
Wouldn't the ball apply force to her foot?
Absolutely it will. And we will do that in about 2 chapters. Why what?
So we're
What is he whying? I don't know. Do you know? There isn't another force right there. That's not what he's asking. He asked if the ball applied a force to her foot, and that would be yes, but then I'd have to draw out everybody diagram of her foot. That makes sense. That's the difference.
so
This is only forces acting on.
the ball stopped. It would exactly like A.
Yes. I'm going to repeat what Jordan just said so all of you hear it because it was not trivial. So we could, if Mira came up here, and I'm not going to make you come up here, but if she did, I could have case A, right? Case B, I push it. Case C, it rolls. Case D, she stops it. And then I could, or that was D, right? Case E could be the ball just sitting there. What would case E look like? Like case A, right? And then she could push it, and we'd have the river. We'd just bounce it back and forth and back and forth and back and forth. You with it there? Yeah. And then we could just go on forever. But the thing that's really important here, in cases B and D, the ball is not in equilibrium, and the ball is accelerating. Okay? In case A and C, the ball is not accelerating, and it is in equilibrium. It's a big deal. What's up?
So, if like you're playing kickball,
Yeah.
someone like rolls it and it doesn't bounce and it comes straight to you, and you kick it at like a split second, would there be no equilibrium on the ball before it goes the way that you kicked it?
The whole time that you're applying a force to it, the whole time that your foot is in contact with the ball, it is not in equilibrium. That is absolutely true. Now, there's also, so I haven't played kickball for a long time.
Yeah.
But when I think about kickball, I recall that when you kick the ball, it's a good idea to kick it up, right? So then you're just going back to projectile motion. Now I have a question for you. You can thank Ben for bringing it up, but I do appreciate it. As that ball, when you're playing kickball, you kick it. So while you're kicking it, that ball is not in equilibrium, right? You're applying a force to it, okay? As soon as that ball leaves the ground and it's flying through the air, is the ball in equilibrium?
Yes.
Draw for me real quick. Here's my kickball. This is sometime after Ben has kicked the ball. Draw the free body diagram for me. Assuming no air resistance, because we're trying to keep our life easier, right? Assuming no air resistance, keeping our life easier, draw the free body diagram for me. Let's say half a second after Ben has kicked the ball. So Ben is no longer in contact with the ball. The ball is flying through the air. Did you guys draw a picture? What forces do you have acting? Yeah. Anything else? No. Yes.
Yeah, you like,
One I were like, yeah, you're asking. Yeah. Josie, do you have a question? Are you thinking? Is that like your thinking motion? All right. It would be accelerating. Sure. It's going down. The velocity changes.
Didn't you mark it as?
I don't think so, but if I did, I made a mistake here. The acceleration is not 0. Is that okay? Yeah. Thank you for checking, because sometimes I make silly mistakes like that. So I'm glad you asked. Yes, it is not, or it is accelerating. Yes to acceleration. Acceleration is not zero. Too many negatives there. All right. So Ben kicks the ball. As the ball is flying through the air do you get a home run in kickball? Is that a thing?
Yeah.
Okay. Hopefully he kicked a home run. These verbs are a little hard for me because I really have not played this for a long time. Kick the home run. There it goes. Let's say how many forces are acting on that ball?
Just the earth, just one.
Just the earth. Just one. So is the object accelerating?
Yes.
Is the object in equilibrium?
No.
No, it isn't. Yes, the object is accelerating. In fact, you can tell me exactly what the acceleration is, can't you? It is. The acceleration on the object is negative 9.8 meters per second squared, right? So this is after the ball is kicked. I just want to make sure we have this in case you're wondering later, like, what was that? After the ball is kicked, FG is pulling down. That's the only force acting. Acceleration is this. F net equals FG does not equal 0. Is that ball in equilibrium, friends? No. Not equilibrium. Okay. How are we doing so far? We're going to write something big down in just a minute, but I want to make sure we're okay with this so far. Okay? So the next thing goes somewhere in your notes that you're going to see it. So don't squeeze it at the very bottom of a piece of paper. This is the big deal right here. Okay? This is it. It's very exciting. So much build up, you're not going to be like, oh, yeah, whatever, I got it. Okay, here we go. If F net equals 0, then tell me about the acceleration. If the net force equals 0, the acceleration is 0, right? I'm going to put parentheses. Right? If F net is 0, then acceleration is 0. That makes sense, right? Okay. If F net does not equal 0, then tell me about the acceleration. Not 0. Not equilibrium. How are we doing? Does this make sense to you? Based on the stuff we just talked about? This right here is Newton's first and second law. Okay? That's it. That's all you need to know. That is Newton's first and second law. Okay? An object in motion, state in motion, blah, 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 blah. That's what you need to know. If the net force acting on an object is 0, it's not going to accelerate. It's not going to speed up or slow down. Okay? If an object has some sort of net force, it's going to accelerate. That's it. You with me? Okay? Simple. Simple, simple. That's it. There's one little piece that you may be asking yourself. And that thing that you may be asking yourself is, but Miss Carbeling, if the net force isn't 0, and I know that it accelerates, how do I figure out how much it accelerates? Is that what you're asking yourself? That might have been what you were asking. If you weren't, then I'm going to plant that seed in your head. That's an interesting question, Ms. Carbeling. If the net force isn't 0, I know it accelerates. How much does it accelerate? The acceleration is just a result of having a net force acting on something. How do I figure out how much something accelerates? Let's think about it. Let's take my basketball, and then let's imagine that I have a bowling ball as well. I've got a basketball and a bowling ball. Tell me about the differences between a basketball and a bowling ball. Compare them for me. You imagine they're right here. Go, what's one of them?
Bowling ball heavy.
Bowling ball's heavier, which means it has more what?
Weight.
It has more weight. You're exactly right. That it has more weight because it has more mass. Does that make sense? Because when we figured out weight earlier today, remember it was just mass times acceleration. So I take that bowling ball and that basketball. Okay, one of them has more mass. Quick question, I want to make sure you're paying attention here. Ignoring air resistance. If I said 1, 2, 3, go, and I let them go at the same time, which one's going to hit the ground first? Talk to your table mates real quick. Go. Which one's going to hit? What did you decide? Which one's going to hit the ground first? The bowling ball or the basketball? Again, ignoring air resistance. Any ideas? What'd you say?
The same time.
Same time what?
Because that's how it was with the most you did.
Because that is not a bad answer. That's exactly right. It's how it was. How many things have we dropped in the last 3 months that we've been together? We've dropped rulers, we've dropped balls, we've dropped frogs. Probably we've dropped other stuff. We've dropped rockets. Now I have a question for you. In all of those cases, we were able to tell how long it took something to fall, right? In any of those cases, did we take mass into account? No! Mass doesn't matter, you guys. It doesn't matter at all. I think there was one problem that we did a while ago, and somebody was like, how does the mass matter? And I said, They said, oh. Yeah. Mass doesn't matter. Mass doesn't matter when it comes to time. Mass does matter when it comes to the acceleration given a force. So this is what I want you to think about. I want you to imagine yourself with a bowling ball and a basketball. They're both sitting on the ground, and you are going to push them both with the same force. What's going to happen? The basketball ball will go farther. Is there maybe a word that starts with an A that you might want to describe that with? It will accelerate faster. Are you with me there? Okay. So I want to think that again. Okay. Basketball, bowling ball, same force. You guys know this because my 2-year-old knows this, or 3-year-old now I guess she is. But she knows it because you do this all the time, right? You push the heavy thing or you push the light thing. You know that the light thing is going to accelerate faster. True? Okay. So we can say that acceleration is dependent on mass. If the mass goes up, what happens to the acceleration? It goes down. Yep. How are we doing? Are we okay? Now I want you to imagine you've got a bowling ball and my 3-year-old has a bowling ball, okay? And you're both going to push them. They have the same mass. I imagine that you as a 16-year-old or plus or minus a couple of years there, okay? If you push on it and my 3-year-old pushes on it, which one's going to accelerate faster? She's not like a superhuman. She's like a 3-year-old. Which one's going to accelerate faster? Yours? Because your force is what? Your force is bigger, okay? So acceleration depends on force. If the force goes up, tell me about the acceleration. It goes up. We're going to put these two things together. Acceleration depends on mass and force. Acceleration goes up When the force goes up, and it's the net force acting. So if you're pushing on the bowling ball, Earth is pulling on the bowling ball, and the floor is pushing on the bowling ball also, but the net force is just going to be you. Okay? But as the mass goes up, acceleration goes down. So it's that inverse, that opposite relationship, which means mass needs to be in the denominator. Okay? As force goes up, acceleration goes up. As mass goes up, acceleration goes down. Okay? This is pure logic. I don't mean this in any way bad to you because I know that you are all brilliant. But you do not need to be a genius to figure that out, do you? Okay? Isaac Newton gets credit for this. He was not the first person to figure this out, right? They have known about this for a long time too, right? The pyramids were built using this principle, right? Cave people knew this when they were moving things. Okay, they know this. We didn't need Isaac Newton to tell us this, but he gets credit for it. This is the other half that goes with these two things. Now you know all of Newton's first and second law. Okay. How are we doing? Are we okay? Okay. I want to, oh my goodness. Okay, so some of your homework questions tonight, actually all of them I think, involve, here's the force, here's the mass, find the acceleration. Can you do that? Look at it, right? What if I asked you, hey, this thing accelerates this much and has this mass, what's the net force? Can you do that? Probably. Okay. I want to point out a couple things because we still have 10 minutes, so don't leave me yet. I've still got time. I just want to make sure that that makes sense because I'm not going to go through practice problems with that. I'm going to let you do that this weekend because I feel like that's something that you can probably do on your own without me. I've got more things that I want to talk to you about. Okay. We're going to do some ranking tests in a minute, but I want to point something out to you because somebody asked this at the very end of the day yesterday, and I can't remember who it was, but I want to address it. Okay. I'm debating whether I want to address it or not. I'm going to because I don't want you to hold on to something that doesn't matter. This is Newton's first and second law. It's simple. It's there. There's nothing really all that brilliant and special about it. It's just truth. Okay? There's one word that I have not mentioned in this entire conversation, and it's a word that you all are indoctrinated to know and to use. And I want you to think about physics in these terms because this is simple, and I feel like that isn't. It's a word that starts with an I. I heard somebody say it. Who said it? It's okay. Say it. Inertia, right? I'll say it one time. That was the time. Okay? That was it. The reason I bring it up, I will tell you that I have other physics colleagues that I know who will never, ever utter that word in their classroom. Okay? I'm not going to be that person because I want to address the situation. I want you to be aware of it. Okay? It is not incorrect to use that word. It's not blasphemy, and it's not something that I'm going to scream about. The reason I don't ever use it, though, is because it leads to a very, very severe misconception. Okay? The word, I'm going to say it one more time, the word inertia just means mass. If something has more mass, it's going to be harder to accelerate. That's it. That's all it is. If it has less mass, it's going to be easier to accelerate. If an object has no force on it, it's not going to change its motion. Not because it has more mass or less mass. Because friends, if I've got, again, no friction, if I've got a bowling ball and I've got a basketball and I give them both a push, after I've let go of them, they're both just going to keep on rolling. Are you with me there? And they're going to keep going and keep going and keep going and keep going and keep going until Mira stops them. Has nothing to do with how big they are. You with me there? Does that make sense? It's kind of a big deal. So I just want you to know this. The pink one, the purple one, the blue one, that's it. That's it. Okay. Does that make sense? I feel like sometimes when I say this, I'm like being very divisive, and I don't want you to be like mad at me because I'm telling you something different from what your, ninth grade teacher told you or whatever. And I don't mean it that way. This is simple. And I feel like sometimes the big words bog things down. I don't want to bog you down. I just want you to understand physics. We should take a look at this problem. So now we've got stuff going on in the X direction, right? That's why I was saying we'll get there. Water skiers are being pulled at a constant speed by a tow rope attached to a speedboat. Because the weight of the skiers or the type of the skis they're using varies, they experience different forces from the water. Okay, whatever. Values for these forces are here. And the speeds are listed. The question asks you to rank the magnitude of the net force on each skier. Why don't you talk to your table? Could draw a free body diagram. Could read the problem carefully. I'll put it up in just a second. Is that okay?
Yes, they have to wish there.
Yeah. This one's kind of a funny one to start with, so I'm going to just kind of pick your brains here. I'm going to ask you to put down an answer on your boards if you have one. And if you're stuck, no judgment. I'm going to give you another one in a minute, maybe by the time. You're trying to figure out the net force. This one's kind of, I don't want to say it's a trick question. Just the mass of the acceleration of that person. Kind of, yeah. Yeah, I'm gonna jump on what you're saying. You're saying we need to look fundamentally what's going on at them, right? Yeah. Yeah. I'm gonna highlight a phrase here. See if that helps. Take a look at what I just highlighted there, friends. The net force acting on, so we wrote down A is equal to F net over M. If you wanted to rearrange that, you could say F net equals A times M. What's the acceleration in A? Why? Oh! What's the acceleration in B? 1. We're going to keep doing this still. You ready? What's the acceleration in C? None, she says. Why? Because there's constant speed. And how about D? Same. This one's kind of a funny question. The key is right here, friends. It's at a constant speed. If it's at a constant speed, then that means the acceleration is 0. And if the acceleration is 0 times anything is 0. So what's the right answer in this case? All equal, and in fact, all 0. It's okay. This is a funny question because it's all about reading that very carefully, right? All right. Let me peek here real quick. Before the bell rings, I want to make sure that you see this homework. There's the homework right there. 132, numbers 3 and 4. 134, number 1. Okay? Those are the 3 homework problems for Monday. Thanks for playing with me today. I feel like we had a good conversation. I hope that you feel that way. If you're angry with me or you want to talk things out a little bit more, let me know. You want to fight with me?